And now I'll cover how we can go after, you know, in code and in practice moving out the areas that vary. So I'll talk about designing behavior components here. So we're going to do this. We're going to use the second design principle, and that is the principle that states program to an interface and not an implementation. So when we're programming to an interface, we're not directly relying on implementation of that interface. So the actual behavior is determined by subclasses that implement that interface, and we can do this, by the use of polymorphism. We can use the interface parent variable, but reference it to the subclass type that we want to actually use. So in order to implement these duck behaviors, what we're going to do is we're going to have two interfaces, fly behavior and quack behavior, with their underlying objects. They're going to be implementing those interfaces. And then we're going to create a heads-a relationship with these interfaces from our application. In this manner, I mean, this makes our application way more flexible, because we can easily extend it by adding additional items here. Also, parallel development, we can develop in parallel, because other developers can be working on a fly behavior, on these behaviors, while somebody else can be working on the actual, the code, for the app. Behaviors are no longer hidden away in duck classes, which is very, very positive. And like I said, very, very importantly, is we can add new behaviors without modifying any of the existing code, and that's huge. So in C# is a little bit different than what they covered in the book. I had to do things a little bit differently, but I'll go in real quick what we have here. I created another project called duck behavior, which is just a library project, and this is where I factored out all behaviors. So I have two interfaces here with their underlying behavior classes. Then I have a duck library, which is our main project that has a duck superclass, or the base class, and then has a mallard duck, redhead duck, and a rubber duck as its child classes. And then we have a duck UI that actually calls this. So how the duck implements these interfaces, we'll take a look at the code here. So actually I used dependency injection already, because it's otherwise very hard to pass these interfaces in C#. So what I did here, I created the constructor. In the constructor, I went ahead and passed quack behavior, or injected quack behavior and fly behavior into our duck class, and then I created a couple of fields for it. And then I have a method, perform quack and perform fly. These are just regular methods, they're not abstract. And then quack behavior quack will do the quacking, and fly behavior fly will do flying. And this will happen for all of our subclasses. So that's our duck. Then in our behavior, we have interface iQuack behavior, which does the quack, and iFly behavior that has a fly. So quack sound, for example, implements this iQuack behavior interface, and does quack sound when a quack is called. And squeak does squeak sound. And similarly for fly behavior, fly with wings, I'm flying, fly no way. So now the duck has a relationship to these two interfaces, but it doesn't implement them, doesn't new them up. They're completely coming from they're injected here. So in our program, I actually went ahead and created an inject as just a little exercise. And instead of having to new up our Quack sound, I was able to bind it through the kernel, through the ninject, and then just get the instance here, instance of the Quack sound, and just send that instance on down when I created the Mallard duck. And the same for squeak behavior. So when we run this, see Mallard is quacking and flying, Redhead is quacking and flying, and Rubber Duck is squeaking and saying I can't fly. And this approach of development is way better. So basically what I did here, I created a family of algorithms. So these sets of behaviors are a family of algorithms. They can easily be interchangeable. And you can use both of these algorithms. You can see the client can use both of the algorithms. And this is an example of, using the behaviors of the duck, but it doesn't have to be behavior. It can be, for example, similar technique would be used to compute state tags by different states. So this technique that I actually use is called composition. So in our case now, duck class A class has a relationship to iFly behavior and iQuack behavior, to which delegates flying and quacking. When two classes are being used like this, we are using composition. So we actually use composition to achieve the result here that gives us basically this pattern. So instead of inheriting their behavior, the duck class get its behavior by being composed with the right behavior object. And this gives us our third design principle, and that's always to favor composition over inheritance. It's very wise. Favor composition over inheritance in the cases like this, especially when we have items that might be changing. Favoring composition gives us a lot more flexibility. We don't have to keep making changes to existing code, which is huge. It's very easy to change behaviors too. We can plug one out, we can add another one, we can add a whole another set of behaviors through another interface. We can easily change the behavior, extend it, and composition is used in many design patterns. It's like a basis for many design patterns. And then finally, here we go with the definition for strategy pattern. The strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. So that's what we basically did. We defined a family of algorithms. In this case, these algorithms were behaviors for the duck, such as quack and fly. They don't have to be, in our case, we just find out which behaviors are the behaviors that need to be factored out. Then we encapsulate them and make them interchangeable. That means that we can plug one out, plug one in without any changes to the client. Strategy lets the algorithm vary independently from clients that use it. So basically, you can do things with them without any consequences to the client, pretty much. And then a little more talk about the strategy patterns. A shared vocabulary is considered to be a set of understandings that are used within a certain industry for easier and better understanding of the work. So design patterns are in a sense shared vocabulary for in a web development world. We can more easily communicate with other developers. It also elevates our thinking about architectures by letting us think at the pattern level, not at the nitty-gritty object level, which is also very useful. So knowing object-oriented basics does not make us a good OO designer or developer. Good object-oriented design follows solid principles that are reusable, extensible, and maintainable. Patterns help us build systems with good OO design qualities. Patterns are proven object-oriented experiences. Most patterns and principles address issues of change in software. That's a big one. Most patterns allow some part to vary independently of all other parts. And this is the final video of the strategy pattern, and I finally got a really good understanding of what it is.